Everyone, this is a video on balancing chemical reactions. I'm going to start by going over a bit of fundamentals, some background as to why we're doing it, why it's important, just so you have a better understanding of the overall picture. And then I'll get into some specific examples of balancing equations using various methods. Feel free to skip ahead if you want to skip the background. I'll have the timestamps below. So where are we? Let's get into it. All right. So before we get started, just some brief background. So, say for example, I had a hypothetical atom or element, and let's call this element A, right? This could be anything, any element on the periodic table, right? This could be hydrogen, this could be sodium, right? Fluorine, whatever you name it. Let's just call it right now element A. And say, for example, I wanted to combine multiple of the atoms or elements A, right? So this element A is just kind of floating about, and I want to put two of them together. I can do that, and then I'll form something known as a molecule, where I have these two A atoms that are bound together. They're bonded. They behave as one cohesive unit, right? So here I have one molecule of A2 that is composed of 2 moles of these A atoms right here, right? And this behaves as like a unified structure, right? So it's not the most easy to kind of break them apart after we have made them. But essentially, we denote any type of molecules or bound atoms with this notation. And note the subscript here, right? And say I have this A2 molecule that's kind of floating out and about, and I want to attach another element, let's say element B. Well, I can do just that. And I can form something called a compound, which is just, all of these bound together. So say they're bound in this particular manner. But again, it all behaves as one cohesive unit, right? So this is essentially 1 mole of this A2B molecule, but it's composed of two A atoms or 2 moles of A and 1 mole of B here, right? And so when we're talking about these kind of just chemical reactions and stuff, we simplify them into formats just as I was talking about, right? So say I wanted to combine two A atoms. So I have 1 mole of A atom, another mole of A atom, and I combined it into this 1 mole of this A molecule. But again, it's just composed of the two A atoms. So I have two A's going in and one A going out. Another way that I could write this, instead of doing A plus A, right, I could write 2A, right? It's just like a math equation. You read it from left to right. So instead of saying, it's A plus A, well, that's just equal to 2A, right? So I'm looking at this. I have 2A on the left side and then A2 coming out. And here's just another example showing that we can make various compounds in general. But overall, chemical equations, whatever you see on the left side, it's known as your reactants. Whatever you're getting out on the right side is known as your products, right? Again, we read this like a math equation, left to right. And for the sake of just simplicity, you can think of this arrow as an equal sign, right? The arrow is just showing which direction the reaction's going. Later on in your courses, you might see some, arrows maybe going in both directions or something. Don't worry about that for now. For now, we're just saying, all right, this is an equal sign. We're reading it left to right. And we're going always from the reactants on the left side to our products on the right side. And it doesn't necessarily have to be combining two atoms together or, making, synthesizing new compounds. It can be a variety of things. So say, let's take this example up top right here. I'm just splitting apart this. I'm starting with A and B bound together. And then whatever my reaction is, I'm just separating them at the end, right? So I'm starting with A and B and I'm ending with A and B, but they're separate here. And the same with this example here. I'm starting with A, B, and C, but I'm just simply rearranging them, right? I'm just swapping out the position of the A and the B here. So I'm reordering which molecules are bound to what. And here's just another example showing, you can have A and B bound, C and D bound, and you can just rearrange where they are in this equation. But essentially, if we look at this, there's one thing in common. It's that whatever we are putting in on the left side, we are getting out on the right side. All of these equations are following what's known as the law of conservation of mass, and that states that matter can't be created or destroyed in a chemical reaction, right? Whatever you're putting in, you have to get out. We cannot just make new atoms out of thin air, and we can't just, Thanos snap and destroy them either, right? If we put something in, we have to get it out. But that doesn't necessarily mean we have to get it out exactly as we put it in, right? You can freely change the form, right? We can, manipulate what's going on here. So I'm putting in A and B here, for example. but I'm getting out, A and D and C and B, but I still have the same things, right? I have one A going in, one A going out, one B going in, one B going out, one C in, one C out, and the same D in, D out, etc. They all follow the law of conservation of mass. It's just that they are rearranged, right? And that's a lot of what chemistry is, just manipulating matter. And so here are some examples of equations that don't follow the law of conservation of mass. So say I put in A and B, we want to combine them together. I cannot get out A2B. Why? That's because, well, I'm only putting in 1 mole of A. How am I going to get out 2 more of A? I'll have to change something there. I have to, fix something's wrong here because I'm creating an A atom out of nowhere. This is written poorly. This is incorrect. Another incorrect example would be, say I'm putting in A and B, and I'm only getting out A. Well, what happened to B? I can't just get rid of that, right? It's somewhere there. So again, this is incorrect. And they're incorrect because they're not balanced, right? There's something wrong with these ratios. Either I need to put in, maybe more of A, less of B or something. But that leads us into the next part of why we balance equations, because we need to make sure what we're writing follows the law of conservation of mass, and whatever we're putting in has to equal what we are putting out. All right, so let's get into actually balancing equations. And for me, balancing equations is one of those things that you really just got to like drill and practice, and you'll eventually develop the intuition to just kind of know how to approach certain reactions or get a lot quicker at solving them. But I think it's really valuable to just see how other people approach it and just kind of people talk out their thought process. So it gives you maybe a little bit better understanding of what you should be doing. So let's start off with this equation here. We have molecular hydrogen, H2. And recall that H2 is composed up of these two hydrogen atoms. So 2 moles of these atomic hydrogen make up 1 mole of this molecular hydrogen. We have oxygen reacting to form water, H2O. So the first thing I'm going to do is I'm going to look through this. Is this balanced? How do I even check? Well, let's just give it a scan through, right? I'm going to go left to right. And before I even do that, this is something that you should do to kind of help you out. I'm just going to make a little table and keep track of what is going in and what is coming out. And so I see here, again, I'm going left to right, looking at my equation, and I'm just going to write down what atoms are in this equation. So I see a hydrogen here. Moving along, I see an oxygen, and I don't see anything else. So, right, our entire equation is just made up of hydrogen and oxygen. And I'm just simply going to count the amount of hydrogen I have on the left side going in and the amount I have going out. So let's start. So I have 2 hydrogens going in. I'm going to write that down here. And I see I have 2 hydrogens going out. All right. That's good. Great. Great. Now let's go move on to the oxygen, because if we have 2 in, 2 out, that's balanced. Let's move on. I have 2 oxygen going in, but I only have, let's see, 1 oxygen going out. So immediately I say, okay, well, this equation is not balanced and we need to do something to this. So how can I balance this? What do I need to do? Well, just like a math equation, I say, look, well, if I have 1 oxygen going out and I need 2 to make it even, what do I need to do to get from 1 to 2? Well, I could just multiply it by 2, right? So I can just come up here. I can say, again, remember this all behaves as one cohesive unit. I can just put a 2 there. Just like a math equation, I'm multiplying like 2x or something, right? So I'll put my 2 here. I'll say, okay, let me go back and let me check. Let me see what's going on. Let me recount. So let me start off with the oxygens, right? So I'll say, okay, now I have 2 oxygens going in. That checks out. And then now I have 2 times 1. So 2 oxygens going out. Good. My oxygens are now balanced. So that's good. But in the process of balancing out this oxygen, what I did was actually unbalance the hydrogen, right? Because I added 2 more hydrogen on the right side. So I need to go back and just double check what I'm doing. So let's check it out now. So again, I'm looking at my hydrogen. On the input, I have 2 hydrogen. So now on the output, I have 2 times 2. So I have 4 hydrogen. So let's fix out this equation real quick. So I have 2 in, 4 out. How do I get from 2 to 4? Well, again, I can multiply by 2. So I could simply just say, okay, well, I need to increase the amount I'm putting in by 2. Again, I'll just put a 2 coefficient right there. and then I'll double check and count everything. So let's recount and see what's going on. So I'm going to just erase everything in this table just to start from the beginning. Say, all right, so I have 2 times 2 is 4 hydrogen going in. And I have 2 times 2, 4 hydrogen going out. Amazing. Great. Love to see it. Now let's move on to the oxygen. I have 2 oxygen going in, and I have 2 times 1 is 2 oxygen going out. So now this equation is fully balanced because whatever I'm putting in, although they're in different forms, it is equivalent to what's going out. So you can see we've rearranged everything, but we're looking at the atoms here. All the atoms I'm putting in is what we're getting out. We're getting equivalent exchange right here. And so this is our final balance reaction. 2H2 plus O2 equals 2 H2O. And just to recap, you can pause and read through this if you want, but this is generally just the steps of how I approach this, starting left to right. And you can look at some of the more complex molecules to start. You can count the amount of atoms and adjust the coefficients, but essentially you'll be left with this final balanced equation. So you can see here that in our initial equation, I don't have anything written up top right here, but in the bottom, I have a 1 written right here. So these are essentially equivalent. Usually when you have essentially just 1 mole of something right there, you don't really need to write it out, right? I could be just as fine leaving out that 1. Just the 1 is assumed to be there. Just like for example, if I'm writing 1x, well that's just equivalent to x. 1 times anything is anything. But if it helps you, by all means feel free to write it. All right, now let's get into some examples and just a bit of practice. And by all means, feel free to pause the video, give it a try on your own. I'll have the solutions there and I'll talk through my thought process. I'm going to start out slow with gradually increase the difficulty. Let's start off here. So I'm looking at this equation. Looks like we have propane here reacting with oxygen and we're creating CO2 gas and water. So first things first, I'm going to just make my little table here, right? I'm going to see what's going in, what's coming out. And I'm looking, okay, see, we have a carbon here, so I'm going to write a C. We have a hydrogen there. I'm going to write an H. We have an oxygen there. I'm going to write an O. And it looks like that's all we got. So we have carbon, hydrogen, and oxygen that composes this entire reaction. So let's start this out. Let's count and see if we're balanced. Do we need to do anything to this? So I'm going to scan left to right. I'm going to start with this, the larger molecule. I just like starting with the more complex ones because a lot of times when you balance those, you'll see that, the equation kind of works itself out, or you can more easily manipulate these species that are just like there together. So I just like tackling these first. So let's do that. I'm first going to look at the carbons. So in my first molecule here, I have 3 carbons. So 3 going in, scanning left to right, no more carbons on the left side. And I go on the right side and I have 1 carbon on the right side. So I'm going to just work as I go here. You could fill out the entire table first before you start balancing, but I find it much easier to just work as I go because again, as I previously said, a lot of times it will just like work itself out. And you'll see what I'm talking about. So I see that I have 3 carbon going in, but 1 going out. So I'm just going to work as I go. How do I get from 1 to 3? Well, I just need to multiply by 3, right? So I'm going to come right here. I'm going to say, all right, let me just put a 3 right there, right? So I'll look again. So what we just did, we put a 3 in front of this whole CO2 molecule. And right, I know that messes up or increases the amount of oxygen as well, but I'm not even going to worry about that right now. I'm just looking at the carbons first. So we have 3 carbons going in, and then now we have 3 times 1, so that's 3 going out. So now we can say that, okay, look, our carbons are balanced. All right, that's good to go. That kind of eases a bit of stress for me at least. Let's move on. So, right, we were looking at this propane molecule, so we took care of the carbons. Now let's go to the hydrogens. Let's see what's going on here. So I have 8 hydrogens going in, no more on the left side, and I have 2 going out. So I'm going to write it down here. 8 in, 2 out. Well, how do I get from 2 to 8? Well, I'll just multiply by 4, right? So again, I'll just look up to here. I'll say, okay, so let me just write a 4 right there. And again, all of this gets multiplied by 4, not just the hydrogens, the oxygens as well. But let's look. Let's go back. We're working as we go, and we'll count. So now I have, again, 8 hydrogens going in. And now I have 4 times 2, which is 8 hydrogen is going out. And again, just remember this 4 means that there's 4 moles of water, so H2O. But if I multiply that 4 out, it's 8 atoms of hydrogen in there. So that checks out. That is balanced there. Our hydrogen is good to go. So let's write in our table. We have 8 in, 8 out. We're good to go. This checks, this checks. And the last thing we have to do are the oxygens. So I'll scroll along. We have 2 oxygens going in. And I see we have 2 oxygens in this equation. But remember, we put the 3 here. So we have 3 times 2. We have 6 oxygens total there. And then we have 1 oxygen here. But again, remember, we put the 4 in front of it. So we have 4 total. So on the right side, we have a total of 10 oxygen atoms. So I'm going to write that in. We have 2 going in and we have 10 out. So how do I get from 2 to 10? I'm just going to multiply by 5. So I'll look up to my equation real quick and let me erase some of this scratch work. I'll say, okay, got to multiply the input by 5. So I'm just going to drop a 5 right there. And I'm going to go back and double check everything, right? Because I didn't change any of the stuff we worked on before. I already know the carbons are good, the hydrogens are good. Let's check out the oxygen. So I have 10 going in, and then I have 6 plus 4. So that is 10. And then so 10 equals 10, and that checks out. So now we have 10 going in, 10 going out. That works, right? So our final equation would look something like this. So I have 1 mole of this propane, 5 moles of molecular oxygen, which is 10 oxygen atoms in there, 3 moles of CO2, and then 4 moles of H2O. All right, now let's move on to our next example. To get the next equation up here, by all means, feel free to pause it and work it out for yourself. But let's give it a go. Again, starting left to right side. I'm just going to briefly do a scan and see what's going on here. Just without even making my table or anything. I see, all right, we got 1 calcium here. We got 1 calcium there. That's good. We have 2 hydrogen there, 2 hydrogen there, so an oxygen. And I can tell this is going to give me some trouble, right? So I know that's going to be the tough situation. So I might want to tackle this first, right? Because if I leave things like the hydrogen for last, I know that I can easily just like put a 3 or something in front of the hydrogen, and I'm not going to mess up like if it has like multiple atoms attached to it, right? Because if I put like a 5 right here, then I'm automatically interfering. I'm putting 5 more calcium, then I got to go here and put a 5, then all this. So I kind of like leaving these ones that are just by themselves for last because I can just adjust those later as needed. But again, let's try it out. Let's just see without really doing the table here. We'll make the table if we need. So let's see. So I'm going to start off with the calcium. I know the calcium's good to go because look, I have 1 here, 1 here. Calcium's good. All right. So now let's move on to the next thing. We have H2O, we have some hydrogens, we have some oxygens. I'm going to start with the oxygen first in this case. Why? Well, it's just as I said, because if I do the hydrogen later, I know I have this one that I can kind of work with on its own after. And by all means, feel free to try the hydrogen first. But for me, just it feels like this oxygen would be better to go for. So I'm going to do that. So I look here, I say, I have 1 oxygen on the left side, and I have the 1, but I have 2. Also, remember, these are little groups that act together. So can't really separate them apart, but I have 2 of these OH groups, right? So I have 2 oxygens total right there. So I have 2 oxygens on the right side, 1 on the left side, 2 on the right side. So what do I need to do? Well, I'm just going to put a little 2 right here, right? Then I just bring it all together. So now I have 2 oxygens on the left and I have 2 oxygens on the right. Good. Checks out. So we have our calcium done. We have our oxygens done. The last thing we got to do are the hydrogens. So let's check it out. Again, I'm going left to right here. So we have 2 times 2. So we have 4 hydrogen on the left side. We have 2 hydrogen here. And we have 2 hydrogen here. So that's 4 on the left side. And so to me, that looks balanced. That checks out, right? Everything is good to go. 1 calcium, 1 calcium, uh, 4 hydrogen, 4 hydrogen, 2 oxygen, 2 oxygen, and there it is. Right, that was a bit of an easier example. Let's move on. I think this one's going to be increasing in difficulty. Yeah, all right. So we have, I think there was this H3PO3. This is phosphorus acid, and then we're getting out H3PO4, phosphoric acid, and I think this is what PH3 phosphine. So let's again, just as we do every time, we go left to right. Let's break it down. And just I'm doing an initial scan. I'm looking, saying, look, I know all of these kind of behave similarly, right? I'm looking around saying, I have a PO3 here. Do I have a PO3 anywhere else? No, but I have an H3 here, and I have an H3 here, and I have an H3 here. I'm like, okay, cool. How would I balance those out, right? I have H3 and H3 and H3. I have two more H3s on the right side. So I'm just going to mess around and put a two right there. Who knows? We'll see. Yeah. So let's put a two in front of there. And then, so now I have two H3s on this side and then one H3, another H3. So a total of six hydrogen here, three hydrogen here, and three hydrogen here. But essentially, I just, instead of counting all the individual hydrogens, I simplified it by just kind of looking at these groups. And that's just like maybe a trick you can learn, start picking up along the way that'll speed things up for you. But essentially, we'll put the two there. We'll see if it works. So that now that I put the two there, I know that the hydrogens are good to go. All right. But let's move along in this compound and see what's going on. So now that I put the two here, that means I have two phosphorus. So let's count the phosphorus in each one. So I have 2p on the left side. I have 1p here, 1p here. So 2 equals 2, and the phosphorus is all good to go. All right. Well, that balanced that out. And the last thing is the oxygen. So again, reading left to right, I have 2 times 3 oxygen. So 6 oxygen on the left side. And let's see what's going on the right side. I have 4 oxygen on the right side. All right. To me, this oxygen is probably going to give us a bit of trouble. So what can I do here? I have more oxygen going in than I'm getting out. So there's less oxygen on the output. To me, that says, okay, I need to do something to this side right here to give me more oxygen. Well, what's the one thing I can do? I can just, add the coefficients in front of it. So I'm thinking, all right, these got to be whole numbers. There's ways you can do it with fractions and work through the math and stuff. Again, I'm just talking through my thought process and how I approach this. So I'm saying, okay, we have 4 oxygen here, 6 oxygen there. Is there like a common multiple or something that we could do? And I'll just like, briefly go in my head. If I put a 2 here, that means I would have 8 oxygen, and that doesn't really match up with the 6 there. Like, well, what happens if I put maybe, I don't know, 4, 5? And I'm just kind of mentally going through just what can I multiply this 4 by to get 6? Like, well, nothing really I multiply 4 by is going to get me 6. However, there's a, common multiple between the two. If I multiply 4 times, let's say 3, well, then that would leave me with, let's see, if I put a 3 there, I'll get 4 times 3 is 12 oxygen there. And then that gives us more than what we have going in, right? So if we recount that, oops, what did I just do? Oh, yeah, there we go. So if we recount that, sorry about that, I'll look at the phosphorus. I'll say, okay, well, the oxygen. I'll look and say, all right, we have 6 oxygen going in and we have 12 going out. Well, that's easy to work with, right? If I have 6 going in, 12 going out, all I got to do is multiply the left side by 2 and I'll get 12, right? So let me try that. So we already have 2 here. If I want to multiply this by 2 again, that'll just give me 4. And then I'll go back working as I go and I'll check my oxygen now. So I'll say, all right, we have 4 times 3 is 12 oxygens. 3 times 4 is 12 oxygens. All good to go. But in that process, we also altered everything on this side, right? So now let's go back and let's double check what we did, right? So I'm going to go and just look at let's pick the phosphorus now, right? So I have 4 phosphorus in, then I have 3 times 1, so 3 plus 1, and that's 4 going out. So the phosphorus is all good. And the last thing we got to take care of is the hydrogen. So I have 4H3 here, which is 12 hydrogen, or you could just say 4H3. And then I'm going out here. I have 3 H3, so 3 times 3, we'll say 9, or we could say, whoops, 3 H3 there, plus, and then we have an H3 here, which is 3 hydrogen, or 1 H3. When we add these, we will get 12 hydrogens or 4 H3s. So when we look at that, everything should add up. So we have a balanced equation right there. And let's check it out. Here it is. four hydrogens. Sorry, four H3PO3, three H3PO4, and then one PH3. And again, I excluded the one right here, but it is implied. All right, and then moving on to our last example, a bit of a more complex one. We have more just complex compounds reacting with each other. We have three things going in on the left side, and then we have two on the right side. So you can see if I put out the table and really just started counting out all the individual atoms there, that can get a bit hectic. It could be a lot to keep track of. But by all means, practice. I encourage you to practice it out because once you just like go in there and you count what's going in, what's going out, that's a solid way to do it. But again, I'm just talking you through how I would look at this and it maybe might help you save some time. So again, I'm just doing a brief scan through this. I'm looking around. I see, okay, got an iron here. I got this SO4 group. That looks like it's kind of just hanging out. Do I have any more? Oh, look, I have an SO4 right here. Like, okay, well, why don't I just start with like, tackle the most difficult thing first? So look, I'm not going to go in there and balance the individual sulfurs and the individual oxygens. I'm just trying to balance this whole group right here. Because I see they have one of them uh, in the reactants and one of them in the product. So I'm going to balance them all together. So look, I have three SO4. So three SO4 here. Then I'm looking on the other side. I have one SO4 here. So again, working as I go, how do I get from 1 to 3? Well, all I got to do is multiply it by 3. So I'm going to put a 3 right there. And again, yes, it does alter all the other chemicals in there, but at least I know it just kind of mentally clears things up for me that this part is kind of taken care of, so to say. But we might need to go back and fix it up later, but we'll see. We're working as we go, and it's more of a trial and error. So I'm going to stick with the same molecule that I was with earlier, right? So the SO4 is done. Now I'm going to look at the iron here. So I have two iron atoms. Scan through the equation. Oh, I got another iron here, but I only have one on this side. So how do I get from 1 to 2? Multiply by 2. I'm just going to pop a 2 right there. So let's check. For me, I see, all right, well, 2 iron here, 2 iron there, 3 SO4 here, 3 SO4 there. So this molecule to me is balanced. It's done, and that kind of mentally clears things up for me. So I'm just gonna go ahead and move on. We might need to come back to this and change something later on, but we'll get to it when we get to it. So now I see, all right, NH3. Are there any other NH3 groups? We have an NH4. So, nah, it doesn't really work, but that's the only other place that I see nitrogen. Why don't we just try balancing out the nitrogens here, right? So let's do that. So I'm looking. I see we have one nitrogen on the left side, three nitrogens on the right side. Actually, no, apologize. Not three nitrogens. It's NH4 times 2. So we have two nitrogens here, but then multiply that by the 3 we put in front. So we have 6 nitrogens on the right side, right? Not pretty. We have this NH4 molecule, and then we have, the parentheses, the 2 around it. That means there's just another one of these NH4 molecules, so 2 nitrogens total. But then we have all of this times 3, so that gives us 6 total, right? 6 on the right side, and then 1 on the left side. How do we get from 1 to 6? I'm just going to multiply by 6, put in a 6 right there. All right, all good. That checks out for me, right? So now we have the iron's good, the sulfate's good, the nitrogen's good. The last things we got to take care of are either the hydrogens here or the oxygens, right? I'm just going to opt for the oxygens. I don't know why tend to leave the hydrogens for last. You could definitely try to balance the hydrogens, but I feel like, there's more of them there. It might get a bit hairy in there. So I feel like it's more easy to kind of work around the oxygen. So I'm going to start here. So I say, all right, we have one oxygen right here. And we could count these oxygens, remember, but we've already balanced this. So I don't really want to mess with it, right? So I'm just kind of looking at this hydrogen. I'm saying, all right, this oxygen. We have one oxygen on the left side, and let's count how many we have on the right side. So again, we already took care of the sulfate, these oxygens at the end earlier. And then all that's left is this kind of oxygen right here. So I have 3 oxygens from that right there. But then remember, I multiplied it by 2. So I have 6 oxygens total in this compound right there. So how do I get from 1 to 6? Well, I'm just going to multiply by 6. So let's do that. Let me erase some of this, clean this up a little bit. So I'm going to put the 6 right there. So now let's just go through, let's double check, see what's going on. So again, iron, 2 iron here, 2 iron there. Done. 3 sulfates there, 3 sulfates there. Done. 6 nitrogen there. 2 times 3 is 6 nitrogen there. Done. Then we're moving to the oxygen. We have 6 oxygen here. And we have 3 times 2 is 6 oxygen there. All right, so everything is good to go except for the hydrogen. So now let's check it out and see what we got to do. So the last thing, I'll just work left to right. We have, starting with this molecule, I have 6 times 3. So that is 18 hydrogens just in this one molecule. I have 6 times 2, which is 12 hydrogens right here. So total, we will have, let's see, 30 hydrogen atoms on the left side. And now let's move on to the right side. So I have 3 hydrogen times 2. So 3 times 2 is 6. Plus, we have 2 times 4. That's 8. 8 times 3 is 24. 6 plus 24 is 30. So 30 equals 30. And it looks like our hydrogens are all balanced on every side. So every species that we have has been balanced. And our final equation is shown right here. So we have 6, 6, 2, 3, 6, 6, 2, 3. That checks out and it looks good. And again, you don't necessarily have to do it the way that I'm doing it, right? I chose the oxygen first just because I know from experience that a lot of times sometimes it works out with the hydrogens and certain compounds. Again, it's what I was talking about with developing that intuition. Just from like drilling these and going through the practices, you gain that kind of extra sense of where to go about these. But again, if you want to, by all means, put in that table and go what's count, like just count what's going in and what's going out. Anyways, I think that was, yeah, that is all I had for this. Please let me know if this was helpful at all, or if you have any specific examples you want me to go through, I'll be more than happy to do so. And I hope this was helpful. Bye.